Hello everyone, my name is Seong-Gyun Leem, and today I will introduce our research that focuses on how to deal with the noisy speech for speech emotion recognition in real-world environment. So why we do this work? Detecting an emotion from a recorded speech is a useful technology that can be applied to various services like entertainment. Excuse me. Is the razor point working? Okay, like entertainment or daily healthcare system. Such useful services can be provided to the human's daily lives by deploying the SEL system on devices like smartphone or smart speakers. However, when deploying the SEL system on real-world applications, we have to consider that there are many types of complex background noise in real-world environment. People use their devices in various places, and in the real-world conditions, those environments are highly likely to contain complex types of background noise. Such background noise can degrade the quality of speech signal, leading to the SEL system to be hard to detect the emotional information from the recorded speech. So, improving the noise robustness for speech emotion recognition is really important to increase the applicability of speech emotion recognition system. What we try to do is to borrow the semi-supervised learning framework to solve this issue. In this framework, the system continuously records the noise speech samples from the noisy target environment. With this collected noise speech samples, we can simultaneously train this SEL model with the noise speech samples from the target environment and the large amount of clean speech samples from the public corpus. We have focused on the emotional attribute which give us a fine granularity of emotion. We focus on predicting the scores of arousal, balance, and dominance prediction. In this framework, we have to consider that such collected noise samples are not likely to contain their emotional label. Annotating the emotional labels for all of them takes too much time to collect a large amount of collected noisy speech samples. So, we have to investigate an approach that can exploit the noise speech samples without requiring their labeling process. What I want to highlight for this approach is a ladder network-based solution. Ladder network uses a denoising autoencoder architecture consisting of encoder, decoder, and the lateral connection between them. This model can utilize an unlabeled dataset during training, leading to the model to decrease the domain mismatch between the training set and test set. How can they do that? So the model is simultaneously trained to two different tasks. The first task is prediction task. In this task, the encoder predicts the emotional label of the labeled dataset. To regularize the prediction, they add the arbitrary Gaussian noise for each hidden layer. The second task is a reconstruction task. In the reconstruction task, decoder reconstructs the clean representation from the noisy encoder. To reconstruct the clean representation, they use a lateral connection from the noisy encoder and the denoiser in their each layer. So by simultaneously training the model with the prediction and reconstruction task, this model can predict the emotional label as well as containing the information of unlabeled dataset. However, in case of applying ladder network-based solution to our formulation, we have to consider that there is a background noise in our unlabeled dataset. Such background noise should be included in the highest layer of encoder to reconstruct the original speech. Such noisy information can disrupt the emotional prediction, so we explore the idea to separate the noisy information from the prediction task. Therefore, we propose the decoupled ladder network architecture, which decouples the last hidden layer of encoder into two different embeddings. First embedding is reconstruction embedding. Reconstruction embedding is only fed into the decoder, and decoder does not construct the emotional related layers. So this scheme allows the reconstruction embedding to contain the information needed for a reconstruction task regardless of the emotional information. The other embedding is emotion embedding. This embedding is only connected to the output layer, and this embedding is not included in the reconstruction task. So this scheme allows the emotion embedding to exclusively contain the emotional information. The rest of the lower layers are jointly trained with the prediction and reconstruction task, which is same as the traditional ladder network training. So by using this scheme, we can separate the noisy information from the prediction task, as well as keeping the original objective of traditional ladder network training. This model is trained to minimize the summation of prediction and reconstruction loss. To predict the emotional attribute score, we use concurrence correlation coefficient, which is generally called as CCC. In this model, we calculate the agreement between the predictive label and the emotional label. So by using the 1 minus CCC as a prediction loss, we can increase the accuracy of the prediction. For reconstruction loss, we use a mean square error between the decoder and the clean encoder. So by using this, we can allow the decoders to reconstruct the clean representation. We set 1.0 for all of the layers reconstruction loss as 1.0 to equally weighted the reconstruction task during the training. So we tested this model with the clean and noisy speech corpus. For clean speech corpus, we use MSP-Podcast corpus version 1.8. The MSP-Podcast corpus contains a large amount of spontaneous emotional speech, which is collected from the various types of podcast recordings. In the version 1.8, we have more than 113 hours of recording samples. In the pre-processing stage, we remove the segments when they have a background music or overlap speaker in the segments, and the samples are selected when their SNR is above 20 decibel, so we can use it as a clean speech dataset. To use a noise speech dataset, we consider that such noise speech dataset should be resembled to the real-life recordings. In the previous studies, they mostly used method is like they manually add a noise signal to the clean speech signal. However, their resulting signals are highly likely to contain a single type of noise, and their amplitude cannot be varied over the time. Also, to match the duration of clean speech signal, noise signals should be repeated multiple times. Such repeated noise are not likely to occur in real-life recording samples, and also such non-stationary characteristics are hard to be controlled by using the traditional methods. So what we do is we directly record the MSP-Podcast corpus in the simulated noisy recording condition. In the single-word sound booth, we simultaneously play the MSP-Podcast corpus and the noise sound. And then we recorded those mixed sound with a smartphone, which is the generally used devices in real-world applications. For the noise sound, we use a non-copyright radio shows collected from juteradio.com. And in this sound, this sounds contains multiple types of human voice, background music, and various types of sound effects. So such multiple types of sound types can simulate the non-stationarity of the background noise in real-life environment. With this setting, we collected different types of recording conditions by varying the signal-to-noise ratio. So to do this, we differentiate the distance between the recorder and speech sound and the noise sound. To calibrate those two distances, we collected the 1 minute samples of speech sound and the noise sound and calculate the estimated signal-to-noise ratio. So this table shows the two distances and their estimated signal-to-noise ratio for each recording condition. So according to the estimated signal-to-noise ratio, we named each recording condition as a 10 dB, 5 dB, and 0 dB conditions. After collecting the noise speech sample, we transfer the label from the speech corpus, clean speech corpus, because since the noise sound is not related to the spoken emotional information, so we can directly use the original label of the clean speech corpus. So as you saw that we use parallel speech corpus by using MSP-Podcast corpus and the noisy version of MSP-Podcast corpus. We built unlabeled data set to train the ladder network-based model. So we collected samples that are not annotated yet. We regarded the unlabeled data set as a collected noise speed samples from the target domain, so we matched the recording condition of test set and the unlabeled data set. For acoustic feature, we use 6300, 73 dimensions of 2013 compare features, which is mostly used high-level descriptor in speech emotion recognition field. Our baseline model is dense network and ladder network. Dense network is a supervised model, so we cannot exploit the unlabeled data set during the training of dense network. The ladder network can leverage the unlabeled data set during their training, but their last hidden layer is not separated into two different embeddings. All the hyperparameters for training and their number of nodes and layers are identical to each other in baselines and the decoupled ladder network. You can see the detailed settings in our paper. So here is the result. We summarize the average concurrence correlation coefficient over 20 trials for each model and each recording conditions. You can first see that the performance decreases as the signal-to-noise ratio of recording condition gets down. So we can say that there is a detrimental effect of background noise to the emotional prediction. As we compare the ladder network with the dense network performance, in the noisy recording condition, we can see that there is an improvement of ladder network in arousal and dominance prediction. So we can say this result shows that the semi-supervised learning framework can increase the performance in the noisy recording condition. Such improvement is further increased when we use the decoupled ladder network architecture. In the prediction of arousal, there was an improvement by 11.4%, 8.4%, and 10.2% for each recording condition. Such trend is similar to the dominance prediction. So we can see that the decoupled ladder network can improve the performance in noisy recording condition. But however, when you look at the balance prediction model, the improvement is not clearer comparing with the other prediction tasks. So to get an idea of this result, I will introduce one of our analysis. So in this analysis, we try to reconstruct the input feature by using emotion embedding instead of using reconstruction embedding. The reason why is that we assume that emotion embedding will have less information for reconstruction tasks than the reconstruction embedding. So what we do is, after training, we cut the connection between the reconstruction embedding and the decoder and reconnect it to the emotion embedding. And then we compare the reconstruction loss of input features by using emotion embedding and reconstruction embedding. So here's the result. This graph shows the mean square error of using emotion embedding and reconstruction embedding. The black bar shows the loss of using emotion embedding, and the gray bar shows the loss of using reconstruction embedding. So you can see that in the arousal and dominance model, the loss of using emotion embedding is higher than the loss of using reconstruction embedding. So we can say that there are more information of reconstruction in reconstruction embedding comparing with the emotion embedding. But however, when you look at the balance prediction model, the difference is not much clearer comparing with the other conditions. We can say that this result means that the embedding is not well separated in the balance prediction model for the lower SNR condition. So we assume that this result is highly related to the less improvement of decoupled ladder network in the balance prediction model. So our plan is to impose more constraints to further decorrelate between emotion and reconstruction embedding to further improve the decoupled network performance. So in this presentation, we propose the decoupled network, which can improve the performance of speech emotional recognition in noisy recording condition. We also introduced the noisy version of MSP-Podcast corpus, which can simulate the noisy speech samples obtained from the real-life applications. We plan to include the noisy version of MSP-Podcast corpus in our future release of MSP-Podcast corpus. For a clean speech, you can still use it by sending the request to us. So if you are interested in it, please visit our website and send us a request. Thanks for attending this presentation, and I'll open the Q&A session now. Thank you very much.
We have time for questions now from the audience first. Please come here.
1, 2, 3. So thanks for the presentation. It was really interesting. So I have basically 2 questions.
Yes.
So first one is for MSP-Podcast. Is it annotated, I mean, in terms of valence, arousal, and dominance, like with some rate? Because usually it's like the like plot or something. I mean, if you annotate it as a valence, arousal, and so on, the audio, you have some time steps to annotate. Yeah. So at which rate do you have for 1 second, for example? How many annotations in 1 second?
Actually, among the continuous recordings, we segmented the samples as 1 sentence, and then we asked to recorders to annotate emotional attribute scores for 1 sentence. So I would say that those scores are from the total of the entire of the 1 speech sentence.
Okay, and sentences like, I don't know, 5 seconds or so? Or
yeah, mostly like 5 seconds, and their range is like 2.75 seconds to 11 seconds.
Okay. So, I mean, so on the second question, yeah, yes. Thank you. So the second question is, so the compare 2013 feature set is usually calculated for whole the audio.
Yes, right. So we use 1 representation per 1 sentence.
Yeah, okay, so now I see. And so you calculated CCC for whole the sentences, I mean the...
yeah, whole the sentences. So there are 1 predictive score for 1 sentence, and there are 1 emotional label for 1 sentence. So we calculate the CCC between those 2 scalar values.
Okay, I see. Yeah, thank you.
Thank you.
So it was another question. Please, you have to come here.
I might have sort of misunderstood your presentation partly, but did you use only all the sort of noisy recordings, where all of them which you used were created using the method you presented, where you added the noise artificially? Because of course, in the noisy environment, people speak differently. There's Lombard effect, people, and this of course might tremendously interact with the reading of sort of emotional state, because you speak louder and slower and all that.
That's a very good point. So I will say that, yeah, you're right. So environmental condition can affect the speaker's speaking style. But I will say that how do you collect the data sets to simulate the Lombard speech? So we can think about the framework like recruit the workers and put the headphones playing the noise sound and act the emotional speech. But however, in this case, that speech corpus will be highly likely to be an active speech corpus. What we want to do is like deal with the spontaneous emotional speech, because as I said, we want to increase the performance in real-world recording condition, real-world environment, and in the real-world applications, the most of the collected speech samples are highly likely to be spontaneous emotional speech. So we have to select the 2 options. So do you want to simulate the Lombard speech samples, or do you want to simulate the spontaneous emotional speech samples? So among those 2 options, we select the spontaneous emotional speech.
Yeah, thank you.
Yeah, thank you very much.
Okay, there are two questions from the chat. So, sorry. So the first one from Hira Damial, Carnegie Mellon University. How different are the emotion and the reconstruction embedding? What can be done to separate the two embeddings so they learn separate things?
As I understand this question, that what will be your constraints to further decorrelate those two embeddings? So we think about including the orthogonal loss between those two embeddings, like cosine distance between emotion and reconstruction embedding, or we can also apply the gradient reversal layer to remove the to further remove the emotional information in reconstruction embedding. That's what we plan for our future study.
Okay, and the second question from Xiyuan Zhang, Westlake University. Very impressive work combining speech separation and SER. Could you please give more details about the semi-supervised learning mechanism in your proposed network?
Details on semi-supervised learning framework. So let's say about the ladder network. So ladder network is, as I said, the ladder network is simultaneously trained with the prediction and reconstruction test. The reason why I say that ladder network can minimize the domain mismatch between training set and test set is because that we can use the unlabeled data set collected from the target environment. So during the training of semi-supervised framework, we can use a label set for the prediction task, and we can use a labeled and unlabeled data set for the reconstruction task. So you can think like that. We combine the labeled and unlabeled data set during the training of the ladder network-based model.
Okay, thank you.